We are in the middle of this absolutely incredible AI revolution. But this explosion in computing power, it has a secret enemy, a fundamental force that threatens to stop the whole thing dead in its tracks. And that enemy is pure, raw heat. Today, we're going to look at how we're fighting back.
You know the feeling, right? You're gaming, maybe editing a video, or you just have way too many tabs open, and that device in your hand starts to get warm. Sometimes it gets really, really hot. It's something we've all experienced.
Well, that simple warmth you feel, that's just a tiny personal version of a massive global problem. Because that very same heat, multiplied millions of times over in data centers all over the world, is probably the single biggest physical barrier to the future of AI.
To really get our heads around the enormous solution, we have to start small. So let's look at the problem on a scale we can all relate to, the good old personal computer. A liquid cooler in your PC works a lot like the radiator in your car. Seriously, you have this metal plate that sits right on the hottest part of your computer, the CPU, and it just sucks up all the heat. Then a little pump pushes a special liquid, now full of that heat, away to a radiator. Fans blow air over that radiator, the liquid cools down, and then it gets sent right back to the processor to start the loop all over again. It's just a simple, elegant, continuous cycle.
So for any PC builder, this is a huge choice. You've got air cooling with those big metal towers and fans. It's the classic, rock-solid, reliable option. There's zero risk of a leak, period. But then you have liquid cooling, and that is all about performance. For a really high-end chip, it can run anywhere from 3 to 10 degrees Celsius cooler, and that is a massive difference when you're trying to push your hardware to its absolute limit.
Okay, so let's level up. What happens when you're not just cooling one little processor, but multiple, insanely powerful graphics cards? You know, when you're essentially building a mini AI server in your house. Well, this is where things start to get really tricky.
And you don't have to take my word for it. This quote from a user on Reddit just nails the problem perfectly. The backplate VRAM they're talking about, that's the memory on the graphics card, and it gets insanely hot. So when you stack these cards, the heat from the bottom card's memory gets sucked right into the fans of the card above it. They end up just breathing each other's hot exhaust. It's a total nightmare.
You see, the design of the cooler itself is everything. Most gaming cards are open air, which means they just dump their hot air right back into the computer case. That's fine if you have one card and a lot of airflow. But blower-style coolers, they act more like a chimney. They suck air in and shoot all the heat directly out the back of the case.
And this table really just breaks it all down. With those open air cards in a multi-GPU system, you get this chain reaction. Card number 1 heats up the air for card number 2, and so on. Pretty soon, they all start thermal throttling, which is just a fancy way of saying they slow themselves down to keep from melting. But the blower cards, they're self-contained. Each one handles its own heat, which makes them pretty much the only way to go if you're air cooling a bunch of cards packed tightly together.
Now that whole power user dilemma, that challenge of keeping just a few GPUs cool in a box, that is a perfect miniature of the crisis facing the entire planet as we build out the infrastructure for AI. So let's zoom out, way out.
This is the number that changes absolutely everything. It's why we're even having this conversation. Liquid, specifically water, can absorb and carry away 3,500 times more heat than the same amount of air. It's not just a little better, it's on a completely different planet. It is a thermal superpower.
And this is where we need that superpower. Welcome to a modern data center. And forget the name cloud. It's a physical building packed with row after row of server racks. And every single one of those servers is cranking out an unbelievable amount of heat. These buildings are basically the world's most sophisticated furnaces. This chart shows you exactly why the old ways just don't work anymore. A standard server rack cooled by air can handle maybe 15 kilowatts of heat. If you get really fancy with containment, you can push it to 30. But the next generation of AI hardware, we're talking 200 kilowatts or more per rack. Air cooling doesn't just struggle at that point, it's physically impossible. It just can't keep up.
So, if air can't get the job done, what can? This brings us into the wild world of industrial-scale liquid cooling.
Okay, so the first approach is kind of a hybrid. A rear door heat exchanger is basically a giant radiator that you bolt onto the back of a server rack. The server's own fans push all their hot air through this liquid-filled door, which cools the air down instantly before it ever gets a chance to heat up the rest of the room.
The next solution gets way more direct. It's called direct-to-chip cooling. and it's exactly what it sounds like. I mean, just look at this incredible plumbing. Tiny tubes deliver coolant directly to cold plates sitting right on top of the hottest components, the processors themselves. You're removing the heat at the exact moment it's created.
And then you have the most radical, most extreme solution of all: immersion. You take the entire server, motherboard, processors, the whole shebang, and you just sink it. You submerge it completely in a bath of special non-conductive liquid. It's the ultimate cooling solution because every single component is cooled directly and evenly, all at once.
Now, these solutions are incredibly powerful, but they also bring a whole new set of challenges to the table. This isn't just a simple upgrade. It's a fundamental shift in how we build and operate data centers. And this is the question on everyone's mind, isn't it? We spend our entire lives trying to keep liquids away from our electronics. The idea of intentionally pumping fluid through a rack of multi-million-dollar servers, it sounds absolutely terrifying. And the risk is very real, which is why the industry has developed some seriously sophisticated ways to manage it. We're talking about a whole new ecosystem. Higher upfront costs for specialized plumbing, new safety protocols, and specially trained staff to maintain it all. At the heart of it, you have complex systems with sealed connectors and constant sensor monitoring that can detect even the tiniest leak.
So why take that risk? Well, the answer is right here. In a typical air-cooled data center, a staggering 40% of all electricity is used just for cooling. That power isn't doing any computing, it's just wasted on getting rid of heat. That's a huge operational cost and a massive environmental burden. Liquid cooling slashes that waste. So it turns out, the real risk might be not taking the leap.
Which leaves us with a final, fascinating question. The demand for AI isn't slowing down. It's accelerating, and with it, the heat it generates is reaching a fever pitch. As we keep pushing the boundaries of what's possible, are we headed for a future where our most advanced technologies actually live underwater?